So I hope you're not. So Shaun, I'd like to do your talk.
All right. So, all right. Actually, this is the third in a sort of a series, and the idea is to discuss scaling, and basically scaling ideas really go back to pioneers of turbulence. And I guess I should apologize in advance for those of you who might have seen a few of these slides in the previous talks, but I'm trying to make this relatively self-contained, so bear with me. But, okay, so going back to Richardson, we had the idea that you could have scaling over huge ranges. In fact, Richardson proposed his 4/3 law for turbulent diffusion and tested it and believed it would operate essentially from the dissipation scale right up to thousands of kilometers. Well, the subsequent developments by Kolmogorov, Abukov, Korsin, Bolgiano, and others, 40s and 50s, tried to make this more precise on the one hand. On the other hand, by making it more precise, they made assumptions such as isotropy for the turbulence, or that you had more or less homogeneous turbulent fluxes. And at the end of the day, these restrictions were such that for applications of the atmosphere, Kolmogorov, for instance, didn't believe that his law would hold to scales more than about 100 meters. Batchelor in the 50s thought it might go up to several hundred meters. Monin in the 70s, again, his book, Weather Prediction is a Problem in Physics, 1971, I think it was, again, thought it would be several hundred meters, but no more. So what I argued in my previous presentations were that actually you can generalize the notion of fluctuation. You can generalize the notion of a turbulent, well, what is a turbulent flux? So it doesn't have to be at all homogeneous. It could be a multifractal cascade process. You could generalize the notion of scale to take into account stratification in the atmosphere, Coriolis force, and other sources of anisotropy. So you could generalize this law considerably. And what is surprising is that we can generalize the overall framework that comes out of this really up to climate scales, and that's what I wanted to discuss today. Clearly, this is a kind of a real space idea here, but clearly there's a Fourier space counterpart, although the Fourier space, if you look at the spectrum, then you're already specifying a specific statistical moment, second order moment, essentially. So you've got the variance of the observables per wave number then would be equal to the variance of the flux per wave number, then times the wave number to the minus 2h. So this is the second order moment. So you get 2h instead of h, and then the wave numbers are inversely proportional to the scale. So, okay. So if you have if you use a normal notion of the usual notion of scale, say Euclidean distance in space, use isotropic notion, or in time, you just use normal frequency, then you predict these types of spectra for space and time. And I look to, excuse me, yes?
In the previous talk, saw a lot about space and time scales for rotating stratified flow, and mostly rotating flows. Will you be able to build any bridges between that way of looking at things and this way of looking at things?
Actually, not too many today. I made a bit of an effort in that direction 2 weeks ago, I should say. In fact, I'm not really going to discuss much the spatial structure today at all. I want to move to scales where, much longer time scales. So, I guess I should apologize for that, but that was more. Right. Well, so the idea is that these are kind of high, and I gave more material about the the idea of having these high-level laws and the relationship with lower-level laws, which in this case are the continuum mechanics and thermodynamics laws. So there was the idea of the hierarchy, say statistical mechanics, then is a more fundamental theory, and so in various limits you can get thermodynamics and continuum mechanics, but the pioneers of turbulence believed that if you went to high enough levels of turbulence, Reynolds number, that you would get new laws, which would be of essentially this sort. So the idea is there's no contradiction with the usual approaches, and in fact we'll see that, and I showed a few weeks ago, but basically all the weather models, GCMs, reanalyses, they all, in fact, satisfy this equation rather accurately with cascading, essentially multiplicative cascades characterizing the turbulent fluxes. So, I mean, there isn't, basically, if this picture is wrong, then the models are also wrong. So, but that doesn't explain the connection, of course. I admit that.
And the model that you're developing applies over a range of scales where there's some flux, something that's cascading. Is that right? Or I mean, like there's a quantity cascading from the global scale to dissipation.
Yeah, the cascading quantity depends on what the field is, and there are presumably several coupled cascades. The main one that is important in the horizontal is the energy flux. The main one that seems to be important in the vertical is the buoyancy variance flux, but then there are other fluxes that would control, say, passive scalars. In the classical case, you've got the passive scalar variance flux, and there are other ones that have not even been identified. In fact, that's one of the interesting things is that maybe I'll jump ahead to just quickly show. I was going to show this a bit later. This is a repeat of. I showed about 10 different graphs of this sort before. All right. Maybe go back one. So I'll go quick. This was a repeat. Whoops, sorry, going the wrong way. This is a repeat of stuff that I gave, in fact, even last week. But the idea of you have the multiplicative cascade. So this is to take into account the extreme heterogeneity of the turbulence, essentially. And this is just this thing called the alpha model. It's a kind of a toy model where you just divide up space by factors of 2 in x direction, y direction, and the vertical then is the density of this flux. The flux, right? The idea is you stir the system at a large scale, and then you've got a cascade of this flux down to smaller scales, and eventually is dissipated at the dissipation scales. So you can model that by having a mechanism which is independent of scale. This would be sort of the inertial range idea. No scale over that range. And then the cascade itself is justified by the locality in Fourier space of the nonlinear terms. So you mostly have interactions between scales a little bit larger and a little bit smaller than a certain scale. So some eddy breaks up into smaller scales mostly because of interactions with scales neighboring. So that's your cascade phenomenology. And then you have a conserved quantity by the nonlinear terms, which is this energy flux. And it's actually a flux, in fact, in Fourier space. But it's better to think of it as a flux rather than as a dissipation, because it only becomes a dissipation when it gets down to dissipation scales. So the idea is that the variability builds up scale by scale, coins, and you have on average, you put conservation constraint so that the area under here, on average, is the same at all scales. So you get these regions where you have violent activity, these spikes, so this is actually your multifractal. Then you look at the fractal set of regions that exceed a certain level of activity. You have one fractal set with one fractal dimension. You look at a region at higher level, say, and you're going to have another set with in fact a lower fractal dimension. And last week I talked about the interesting properties of this, that if you go down to very small scales, in the infinitely small limit, in fact, and then you integrate up, then the effect of all of this small-scale activity is such that you get, from time to time, you get these huge power law, well, they're extreme events, power law tails, and okay, so that was my talk last week. But the evidence for this is of this sort, right? These are from reanalyses, and I gave, I don't know, about 10 slides from different sources: aircraft, dropsondes, LiDAR, meteorological models, different various reanalyses, precipitation, radiance fluxes, et cetera, et cetera. And they all have, quite nice multiplicative structures like this. The idea is that the cascade statistics are such that the Qth power, the average of Qth power, normalize it, should behave like this, where lambda is the ratio of scales over which the cascade has acted. And so lambda equals 1 is a scale where there's no variability. And you can see if you take log of m against log of the scale, then the slope is this k of q, which is some convex function. And the point is that all these different statistical moments, they point, if you like, these lines converge at a point, which is the point at which the cascade is the effective outer scale of the cascade. It's the scale at which the cascade would have started in order to explain the variability at all these other scales. So you can see that on the one hand, it scales 10,000 kilometers to 20,000. Here there's a bit of a deviation, so it's not perfect. On the other hand, the outer scale is a little bit larger than 20,000, which is half the circumference, and that is because at 20,000 there's still variability due to interaction between different fields. So here you've got the zonal wind, meridional wind, temperature, humidity. So there are some differences, and you can go through and quantify all these differences. But basically, if you believe the reanalyses, you believe the data, then there's no contradiction between these sort of higher level laws and the equations, because, well, in this case, the reanalyses, of course, are heavily dependent on the equation. Basically, it's actually a rather special 20th century reanalysis going back to 1871. It's based, in fact, entirely on surface pressure and monthly sea surface temperature data. But all right. Right. So okay. So that will save me discussing it a bit later. But today I will discuss extensions of the cascade, space and time, into actually quite long time scales. But let me first review this issue of the time scales and try and discuss what it is that we mean by climate. And essentially, modern definitions of climate are something like this saying, or climate is what you expect, weather is what you get. It's close to something that Mark Twain said in the beginning of the 20th century, but apparently it's not. Anyway, this is the oldest citation that I could find, Robert Heinlein. But so this is kind of a non-scientific way of saying what the IPCC says, which is climate in narrow sense is usually defined as the average weather. Okay, so it's that kind of an idea. But in fact, I tried to argue rather rapidly, but do that again, that the climate is in fact not at all what you'd expect. That this is not really what you actually expect is something a bit different, which is macro weather. So this is again a bit of a repeat, but I have two data sets here. I have essentially this reanalysis. This is temperature spectrum from 6 hours to 138 years. Of course, you can see a strong annual spike and 6-month spike. And then I've also compared with this GRIP Greenland ice core oxygen isotope surrogate for the temperature. And that goes to 240,000 years. Part of it, the more recent part, has been digitized at a higher resolution. So it looks like there's 3 curves, but in fact these 2 curves are from the same site. But this is the top 91,000 years, in fact, and this is the whole thing. But so there's one calibration constant for the surrogate, so I moved up and down so that they agree here. But the idea is you can see there's basically well, you might call it, well, this is called background spectrum because people have been mostly looking at spikes. Essentially, these are the various important orbital forcing, Milankovitch forcings, and you can see there's some evidence for them, although it's pretty weak. And in any case, the Milankovitch forcing frequencies clearly don't have a very, very large fraction of the variability. Almost all the variability is in the background. The scaling part, Carl Wunsch 10 years ago tried to quantify that by considering that maybe these could be broad lines, and even being very generous, he concluded that there was less than 10% of the spectral variability over this range was due to the Milankovitch forcings. That doesn't mean that that's not important, because you could have various mechanisms where, say, the 100,000 year, which is the main one, 100,000 year variability is a kind of a pacemaker for the ice ages, but it's not at all a trivial or solved problem. In fact, interestingly, if you go back, there are series that go back 2 million years, and you see from 2 million years to about 800,000 years ago, you see a very, very strong spike at 41,000 years corresponding to the obliquity signal. I mean, it's a very, it's sort of almost a textbook. The spike is very, very narrow, and it's about 10 times or more the background. You don't need sophisticated techniques to show it, but then in the last 800,000 years, the things are not at all clear. So, okay, but didn't want to get into that too much, but this is, okay, so you have a climate regime here, maybe 100 years or 50 year to 100 years and lower and longer times, and then you have this intermediate regime, which goes to something like 10 days, and then you have this weather regime here. So I'm going to try and explain these various transitions and see how we can take this framework of scaling and based on these turbulent fluxes, in fact, and extend it over this range. So, okay, and I guess I show this, but again, the statistical character are quite different. If you look at short scales here, the resolution is 15 hertz, so each data point is 0.067 seconds, and you can see the signal kind of wanders around. Turns out that if you look at this in real space, the average fluctuation increases with time scales to some power h, which is something like 0.4. So the longer you wait, the farther the curve changes, the more the curve changes. Of course, Brownian motion would be Gaussian with h is 0.5. You do this up to an hour, so the whole series here goes for something like 2 months. And you see the same type of behavior. But when you get to 20-day averages, so now we're averaging out all of the weather stuff here. We're looking at averages over here. The spectrum is much shallower. So in fact, we have another exponent, h, which is now negative, minus 0.4. Oh, sorry, this should have been up here. You can see that if you first get, say, a fluctuation quite negative, decreasing, then it's compensated quite rapidly by something positive, negative. So you could imagine that if you average this more and more, that the fluctuations get smaller and smaller. And actually, indeed, they do, but only to a point. So actually, so this behavior is what you're seeing corresponding to this part of the spectrum here. But you would think that, if you average this more and more, let's say you took data at a 100-year scale, that there'd be practically no variability. But if you do that, you take data at a 100-year scale, each data point here is a century, then again you see this kind of growing fluctuations. So the climate, really this 100-year series here, is very, very, in fact, quantitatively, this exponent h is almost the same as in the weather regime. So if you say the weather is unpredictable, then the climate is just as unpredictable, in fact. This is at least for pre-industrial. I'll come back to this question of anthropogenic a little bit, but mostly talked about that last week. But okay, so in that sense, okay, whoops, all right. So this is the transition. So something like 100 years. So you do indeed, things do converge up to about 100 years, 3,800 years, and then they stop converging and diverge. So you could look at this in real space by using an appropriate definition of fluctuation that I'll discuss momentarily. But you could look at, say, the RMS fluctuation of this is data at some place in Wyoming. It's it's hourly resolution. You can see weather regime roughly, and then 10 days it goes down. And if you then take the average of, this is actually at 75 north because this is where the Greenland data was, but 2 by 2 degree resolution for a reanalysis, and you get this type of behavior. And then if you look at, this is this Antarctica surrogate, the temperature fluctuations go up again, and so you can see that, and they have to go up. The reason we know they have to go up to this height is because this is more or less the amplitude of the ice ages. Okay, so this is what I call, and this is more or less the time scale of the ice ages, 50 to 100,000 years. And so you can read off on this the typical fluctuation size, but what you see is that it goes, you average, goes down, 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 down. Minimum is something like 30 to 100 years. So this corresponds to this arbitrary 30-year climate norm period, and then it starts to go up again. So the problem with the climate then is how do you reproduce these growing fluctuations? And I'll come back to that. Okay, so you have roughly power laws in these different regimes. You can even, this one is not very well, we'll talk about the regime past 100,000 years, but okay, so this is the type of character of these regimes. And so in this sense, okay, the weather regime, fluctuations grow with scale, they're stable, the weather is what you get, macro weather, macro weather is what you expect because you average more and more, or in this regime, and the fluctuations get smaller, but then the climate regime. So, okay, so the climate is indeed not what you expect. All right, but part of the problem, part of the reason that this was not recognized earlier, because basically analyses of this sort have been around since the 80s, but the significance wasn't really appreciated, and I think is largely because data analysis techniques were not so clear. And there's nothing at all wrong with doing a spectrum, but the interpretation is not so simple. And there are other techniques that have been developed, of course, wavelets and detrended fluctuation analysis. There's various techniques that have been developed to try and well estimate exponents when you have a scaling regime, but the interpretation, say, of a wavelet coefficient or the scale function in the detrended fluctuation analysis are not simple to interpret, and people have basically missed all kinds of stuff. So what I am proposing is something very, very simple. You've got differences, right? You can define fluctuations as differences. The mathematicians, of course, call this the poor man's wavelet because it is indeed a wavelet, but one that they find contemptibly uninteresting. And all it is, of course, is say the difference between the value of your, say, time series temperature, say now, and t plus delta t. Problem with this is that it only gives you good estimates of exponents when the scaling exponents are within a narrow range. In fact, between this h value between 0 and 1. Basically, the differences on average can't decrease. So h, and they can't increase more than linearly. So there's a limit there. You could define a thing called a tendency fluctuation, which is basically you take your series, you remove the overall mean, and then you see how on average do you calm down the fluctuations by averaging more and more. So this would be appropriate in the regime where the fluctuations are canceling out, and in fact it only works between 0 and -1. So these two are very limited and cannot be used for this whole regime, the atmospheric regime where you have both weather, macro weather, and climate, positive, negative, and positive exponents. But there's a very simple solution, which is, in fact, mathematically a Haar wavelet. You define fluctuations based on that, and all that is essentially the difference of the average of the first half of the interval minus the average of the second half of the interval. So basically what happens is when h is positive, the averaging doesn't matter. You're really looking at a difference. And when h is negative, the differencing doesn't matter. You're looking at the effect of the averaging. And so you can easily interpret this, and that's what allows me to get these this huge range here, so you could actually put then, the RMS value. You could look at other statistical moments if you're interested in multifractality or whatever, but so you could really read off the values of these fluctuations, and it's quite physically meaningful. All right, so very quickly then, if you want to compare to other techniques, so you have a spectrum, fine, that works for any range of H. H up here is it's the average fluctuation. It's related to the spectrum. The spectrum is a second order moment, so there's an extra multifractal correction that I won't talk about, but basically the H and the spectral exponent are related. So there's nothing wrong with spectra, but again, it's not, this interpretation is not so straightforward. In the red box, I've put these simple to interpret fluctuations, which the HAR is the one the most, but so then there are others. You've got all kinds of wavelets, of course. Mexican hat is a popular one, but and there's the detrended fluctuation, et cetera, et cetera. But these have no straightforward interpretation, but they are indeed quite good for estimating exponents. In fact, the HAR is just as good, say, as the detrended fluctuation analysis, for example. So what this allows you to do then is to make these huge composites. So maybe this is a bit exaggerated, but you can put together then, you can get a really a huge range of timescales here. And you can really see then the temperature going up to 10 days, down to 100 years, and up again, down, and then over here, this is subject to, this is from benthic oxygen isotopes using this sort of more or less official calibration, but the interpretation of this signal in terms of temperatures is questionable. So you may not want to take this part here too seriously, but the rest of this is quite reliable, or believed to be quite reliable. You could also compare the effect. If you do spatial average, you get, say, a global average temperature, then, of course, the variability is much lower. You still have the transition from weather to macro weather, but it goes down very slowly. And then the other thing you can see is that there's actually a difference. This is actually pre-industrial, and this is industrial. This is from proxies. And so you can see that the transition is not at the same scale, and I'll come back to that. But okay, the basic stuff is the same. All right, so how can we understand then the macro weather regime? It's this transition at about 10 days, and there's a fairly straightforward way of doing it, because I said this energy flux is basically dominating the horizontal velocity statistics, and the velocity is what you need to go from space to time, dimensionally speaking, and of course physically you have advection. So what you have to do is estimate then this energy flux. So you can do that by considering the solar heating at the top of the atmosphere, average it over night and day and latitude or whatever. You can estimate the amount, the fraction of that solar heating that is transformed into mechanical energy, essentially wind energy, something like 4%, and you get about 8 watts per square meter. You can then say, okay, if that energy is distributed roughly evenly over the troposphere, which is actually not such a terrible approximation, you can check it. So I say, let's say the lower 800 millibars of the atmosphere, then you get a mass per area, which is about 8 tons per square meter. You take the ratio, and you get about a milliwatt per kilogram. So with that, then you can use the length scale, half the circumference, plug it in, and you find that you get about 21 meters per second for the velocity difference for 2 points on opposite hemisphere, or opposite sides of the Earth, and that's actually very close to what is observed. And you can then just take the ratio and get a time scale, and that's basically the time scale of these large planetary-sized structures, and it's about 10 days. All right, and you can see, this transition is, you find this more or less everywhere so this is what? Humidity, zonal wind, meridional wind, temperature, so 10 days, and this is about, this is 10 years here, you get some. Okay, but you get the same basic kind of stuff. If you look at temperature in particular, you can see you get, this. It's a little different than it's often assumed that this transition is associated with, or can be modeled by Ornstein-Uhlenbeck processes, And that spectrum goes from essentially -2 here, instead of 1.8, and to 0, so it goes flat instead of, say, 0.2. So there's there's a sort of a slight difference there, but so that's some kind of approximation. But in fact, it's not that accurate. The other thing you can do is say, well, the ocean is also a turbulent system. There's evidence that the current spectrum is dominated by the energy flux there, although the evidence isn't as good for the atmosphere. And you can then look at drifter data and estimate this epsilon as 10 to the -8 instead of 10 to the -3. And you put that in the formula, and you find you should get a transition about a year. And so you get essentially the same type of ocean weather, essentially the same spectrum as real weather out, but it goes out to a year. And then the lower frequencies have a slightly different slope. Interestingly, you can do this on Mars as well, because there's an issue. I mean, the main explanation at the moment for this transition is an argument to do with baroclinic instabilities, most recently put forward by Vallis a couple of years ago. But that doesn't work near the equator and doesn't actually give you a very accurate estimate. So anyway, but it's worth trying to check this, say, on other planets, in this case Mars. And so we used some Viking data. And you can work out purely theoretically, because, what the spectrum should be on Mars compared to Earth. So you can look at the ratio, say, the energy fluxes. You can work it all out theoretically, knowing the pressure across the Martian atmosphere compared to the Earth atmosphere, the planetary radii, distances from sun, planetary masses, albedos, etc. And you can work out there should be a shift in spectra in the frequency of this much and the amplitude of that much, and then so you can superpose. This is a spectrum from Fairbanks, Alaska, and this is on Mars, and so you can see that you get really excellent agreement. There's no adjustable parameters here, right? This is just a theoretical shifting of the Martian spectra on top of the Earth spectra. And these spikes are basically just the daily Martian daily in this case spike, and then the harmonics. This is the Earth daily, etc. Okay. So, all right. So, how are we going to extend this model that I discussed last time, this fractionally integrated flux model? I'll say what that is in a moment. Again, how can we extend this to try and account for this macro weather regime and eventually the climate? So, right, I just went through this. So this is the basic idea of the flux being a cascading quantity, and this is some of the evidence that indeed it is cascading. You can, of course, if you have a multiplicative cascade, which is what those results indicate, then you can model that by the exponentiation of an additive process. So if this is your flux, then there's a generator of the cascade, which is additive. So you could take, say, an IID Levy noise. Alpha is 2, then you have just a Gaussian. Otherwise, it's, in fact, an extremal Levy. You convolve that with singularity of a certain order. This is actually a fractional integration. And you get then the generator, and if you put that in, you exponentiate it, then you get statistics of this form with exponent depending on the Levy index, and then this codimension of the mean, which characterizes the intermittency. This is the same as just a fractional, it's just the same as a power law filter of the noise. So some level, all you do is you take your noise, you filter it appropriately, power law filter, and then you exponentiate it. And then that's the model for the turbulent flux. But the actual observed process, say the temperature of wind, is related to the turbulent flux. There's it's like delta V is epsilon to the 1/3, delta X to the 1/3. There's this extra scaling, and that can be taken into account by essentially it's a linear scaling operation, just another fractional integration, a convolution. So again, in Fourier space, it's just a filter. And when you do that, you get fluctuations. This would be the qth order structure function, which has exponents like this. So you have a kind of a linear part with this h exponent I discussed earlier, but then you have a convex part due to the turbulent flux multifractality. Okay. So, all right. So that's just a recall of what I described as a model for the weather regime. And I skipped over the fact that, all right, there's all this anisotropy, the vertical structure, and that was discussed 2 weeks ago. But so, okay, so clearly one can't just use isotropic notions of scale if only because the vertical is totally different in statistics and in physics than the horizontal. All right, so how could what's the obvious way of extending this model further to go to lower frequencies is simply to consider a space-time cascade, but a cascade that starts at much longer time scales than the time scale that corresponds to the lifetime of the larger structure. So instead of saying it's 10 days, let's extend it to perhaps 100 years. And so then you can look at these convolutions, and they can be decomposed into parts where, in fact, you get contributions from the spatial degrees of freedom and temporal degrees of freedom. And then for the very long time scales, essentially the spatial degrees of freedom are no longer important. So you get, they're sort of quenched, if you want to use a statistical physics jargon. And you get what you could call a dimensional transition. So instead of fluctuations in x, y, z, t space that are important, it's only basically more and more, it's just in the time domain. So this just sort of gives you the idea. But a consequence then is that you have this additive, you have two components which are more or less statistically independent for the weather and macro weather. So that's the time scales longer than 10 days. And that means that the energy flux then is multiplicative. And actually, this macro weather flux component actually doesn't depend on spatial scale at all. The spatial degrees of freedom have been completely killed, and I'll come back to that. So that's an unsatisfactory feature because that would predict that if you took monthly averages, say, data, there would be no spatial variability, and obviously there are climatic zones, and they're very important spatial variability. So something has got to be added to this model that I'll come back to. But you can just see purely theoretically, by just extending this cascade, you can predict, for example, autocorrelations. Quite interesting. You get exactly delta t to the -1, which therefore has both low frequency and high frequency divergences, and in fact, you get exponents which depend, in fact, to some extent on the range of scales. So it's kind of a rather interesting behavior, but the exponents you get are very, very close to those that are observed, in fact. So so this is just to kind of come back to where are we in all this. So we started off classical laws. They're isotropic, so you just use a regular vector norm for distance. So this would be for a velocity fluctuation, for instance. Kolmogorov law is you get with these parameters here, but probably only valid over a rather narrow range, maybe 100 meters. What you can do is you can generalize. You replace the usual notion of distance by a scale function. That's what I discussed 2 weeks ago. That takes into account the anisotropy, especially the stratification. You can then do this generalization. So instead of the flux being more or less constant, you make it multifractal. Discuss that. The other generalization I just mentioned is you can make the time scales go much, much larger than the lifetime of structures, and then you get essentially the macro weather. So how do we go further to generalize this even further to the climate? I mentioned those. You have the basic what do we have to do? The problem is that the fluctuations in the macro weather regime are always decreasing, whereas the climate regime, they're increasing. So we need something that will give more variability to low frequencies. Also, the macro weather has no spatial variability, in fact. if you average out the weather scales. So can we just extend this framework? Just to remind you about this transition, so you have kind of macro weather and then climate, something like this would be global temperatures. This is the industrial of the last 100 years or so. You find a transition about 10 years. If you look at data from proxies, but going pre-industrial, you find very similar behavior, but with this transition happening more like 100 years. So, and this is just because of anthropogenic effects, and I argued that actually last week. So this is just to give you, remind you that we have to get this increasing range here looked at. There's just this Antarctica data, so you can then see this is what has to happen. At some point, we know the temperatures have to go through this glacial interglacial window. That's just saying that otherwise the ice ages wouldn't exist. Okay, so there are various estimates, and there's some, of course, uncertainty, all kinds of problems, but somehow the variability has to increase after 10 to 100 years or so. Okay, so what we can do is simply to stay in the same kind of framework, multiplicative framework based on these fluxes, we could say that this is the process I discussed before. This is space-time cascade that I could extend maybe to 100 years or something, and then, in fact, get a reasonable model of the macro weather regime. But I want to multiply it by a space-time, so low-frequency space-time process, which could also be, in fact, multifractal, as we'll see, for the climate. So this could be statistically independent in the simplest model, but it could be dependent, statistically dependent, probably more likely. But okay, so this, I already showed this part here factorizes into a high-frequency weather part, which depends on space, but also this macro weather, which only depends on time. So if I average out, what I can do is if I want to try and test this model, I can average out the high frequencies, and then, so I can essentially, I get this type of, I have a weather process, macro weather and climate, but if I average out, say the scale is larger than 10 days, then the weather process has got very low variability. The climate process has no temporal variability at all at these frequencies less than this 100 years, say, climate transition scale. And so what I'm left with is this type of a factorization, that in the macro weather regime, say between 10 days and 100 years, I'm expecting that I will have a temporally varying flux multiplied by a spatially varying one. Okay, so this is this type of factorization, and that predicts that, say, the spectra will also factor. And so you can test that. So first of all, so this data, 20th century analysis, 6-hour resolution. I just looked at 45 degrees north here, but it goes 138 years. So if I just look at 60-day long segments, and I do average, this is really the weather regime. Okay, so you see this is your wave number and your frequency. There's the structures are oriented in some direction. This corresponds to a wind of, say, typical wind of 72 kilometers per hour. And you can see then the macro weather regime is inside these dashed lines here. Something else is happening. This is just the daily cycle here, these glitches here. But inside here, this is the macro weather. So to look at that, you could take data. I took the data and averaged it over half a month. So the highest frequency then is a month. And the prediction is that this wave number frequency spectrum, that it factors like that, which means that all the isolines, lines of constant spectral density, should be either left, right, or up, down. And you can see that's actually pretty good, except ignore this part in, okay, this is the annual cycle. Okay, this spike's here. And then inside here, I'll come back to this is the macro weather. But outside of here, it's pretty left, right. There seems to be a small slope here corresponding to 30 kilometers per year, so it's a very, very low velocity. But basically, to a reasonable approximation, the factorization works. If you blow up the central part here, then you can see it really does look quite flat, except in this climate regime, which is something like 25 years to 138 years. So, but okay, so it does seem to work quite well. You can check this also in real space. You're saying that the temperature fluctuations should factor into something only dependent on the spatial scale. In this case, it's angle and in time. And so what I've done here is I've looked at averages. This is from this Climate Research Unit temperature series, East Anglia, from 1850. And so you can look at the fluctuations as a function of spatial scale out to 180 degrees. And you can see how does this change as I average more and more. So, and you can see that roughly these curves are the same shape but shifted down by a more or less constant amount, and that holds up to roughly 20 years when you have this transition to climate. So roughly over this range here. Okay, so whether it's, so the temporal scaling is actually quite good over that range. That's the separation between these curves. In fact, the actual fluctuations in space seem to go up a little bit and then down. What this means is that if you look at 2 points, they tend to have more and more different temperature out to something of the order of, this is something like 5,000 kilometers. And then they start to, they become more constant. So this would be a kind of a natural way of defining a climate regime, right? Because what it means is you go larger than about 5,000 kilometers, then you're kind of converging, you're getting smaller and smaller fluctuations, whereas if you go at regions, consider regions smaller than 5,000 kilometers, then the fluctuations grow. All right. So, and you can do, anyway, you can do the same thing for precipitation. All right. So, just to mention, okay, so you have this idea for climatic zones. Now you've got a mechanism, because if you have this extra climate flux, you have a mechanism for getting distinct climate regions. And basically, you just need to have a strongly intermittent cascade process. And this indicates that indeed that's what occurs. This is using the same data, so you could look at the spatial cascade structure in the weather regime here. It's actually relatively low variability, 6 hours, 1 day. But then you go 30 days and 89 years, and the variability gets stronger. Anyway, you can quantify it, but in any case, there's certainly a strong spatial variability here. Okay, so this is what I call atmospheric statistics in a nutshell. According to this model, you could, this is one way to spread. These are the qth order structure functions. So it's the average of the qth moment of a fluctuation. Some quantity, it would go then as some basically constant here times the scale function to some exponent like that. This would be in the weather regime, and the scale function, at least in the horizontal and time, the simplest case could be something like that. This is what I call the canonical scale function. It's just the simplest. A realistic one would involve wind speed and other stuff, but anyway. In the macro weather regime, then you would get the separation, a multiplicative separation into spatial scale function, so the anisotropy in the horizontal, and in the time domain, but the time domain, it actually turns out to be not multifractal, so you really have a linear exponent. And then you could extend this to climate, and at some level, this is a bit almost a guess here, because the data, space-time data in the climate regime, you need lots of data at about 100-year resolution, and very little of that exists. So, but there are some estimates, and okay, so you could, at least for temperature, you can estimate that stuff. So, all right, I wanted to give you one or two. So that's basically the theoretical framework, which becomes quite tenuous, clearly, when I move into the climate regime, but is actually quite well verified empirically up to the macro weather. So, all right, so how can we, so I just want to quickly give you maybe a few interesting applications. So one question you can answer is, how accurately can we measure the climate? So you could look at, here's actually, I took 4 temperature series averaged over the globe. And okay, so they show that, okay, the temperature sort of fluctuations are more or less constant or slowly decreasing to about 10 years and then increasing. And as I argued last week, this is really dominated by the anthropogenic effects, but nevertheless increasing. The interesting thing, so you say how accurately, these different series are all based on quite different, often quite different. The data isn't even the same, and they have different ways of handling the data, filling in holes. And actually, they all have large number of holes. In fact, the best data set here has something like 60% holes, and the other ones have more. So, if you go back to, say, 1850 or 1880. Okay, so what you could do is you could then compare the data sets pair by pair. So if you have 4, you get 6 pairs, and you can look at how do the differences, the fluctuations and the differences change with scale. And you'd expect, naively expect that if we average more and more in time, that we would get a better and better estimate of the global temperature, right? So you think you're just getting rid of noise and error, but actually that's not what happens. You get more or less a constant difference of about 0.1 K. So you can think of that as plus or minus 0.05, half of that. So basically there seems to be kind of an irreducible limit to which we can know the global temperature at the moment. And I've investigated this, and somebody said I don't understand it, but anyway, it seems to be quite a robust result. The other thing is that this is sort of a comment. You can, if you don't want to know the actual temperature at a given year averaged over the globe, say, but you just want to know how do the statistics change with scale, then that can be estimated much more accurately. So the structure functions, the average, say the RMS fluctuation can be estimated to something like 5 times better accuracy. So that's an easier question. Okay, no, I understand, right? Okay. So I just want to give some examples here of how you could, so you could then compare, for example, this would perhaps wake up people a little bit because I'm talking about models here. Look at the GISS. This is a climate model using a historical reconstruction from 1850. So you could have different realizations of that, and you could consider how does that climate model converge to its climate, right? So you're expecting these different realizations. They have exactly the same forcings and everything. The initial conditions are very slightly different. And what you find is that they do indeed converge. The fluctuations get smaller and smaller if you look at the difference, say, of 2 realizations. But they converge in what you might consider an ultra-slow way, meaning there's an exponent is minus 0.15. So you can, if you ran these models for 1 million years, you wouldn't actually improve the convergence an awful lot. So theoretically, they're doing the right thing, but maybe a lot more slowly than people think. The other thing you can do is you can look at the comparison with, say, the data, 20th century analysis. And what you find is that actually, and this is more or less, I guess, what you'd expect, but there's virtually no skill less than about 10 years. So okay, on the one hand, the statistics are very, very similar. All right, so this is the RMS fluctuation as a function of scale for the data and the model. Very, very similar, but they look as though they're from independent realizations of the same process out to about 10 years. But that's what you're expecting, because you're just having different weather, if you like. After about 10 or 20 years, though, the differences get much smaller than the actual value, so you have real skill, in other words. So the models do indeed have skill where, in fact, they ought to have skill, but this quantifies it. You could also compare models and models. Baroque is a Japanese GCM. The Baroque model has this huge anomaly at 2 or 3 years. In fact, several models, such as the EFS model, have this anomaly. It's known but not necessarily well dealt with. The GISS model doesn't have that. In any case, so the Baroque converges roughly the same way to long time scales as the GISS. And so the conclusion is that the models and the data, in terms of their variability, are actually quite similar past about 10 years or less than 10 years. Not surprisingly, they're different. And all right, now what you can do is you can look, well, how well do the models actually converge to the climate, though? So you could take this historical reconstruction, 1850, and you could, to present and compare it to the 20th century analysis. So this is temperatures, and you could look at what happens, what's the difference in the temperature fields at a pixel, which is in this case 2.75 or something degrees resolution. Anyway, you could compare fluctuations, and what you find is it doesn't change a lot. That means that at any scale, there's an error of about plus or minus 2 degrees compared, the model compared to reality. And if you're taking the data as reality, then if you average in time, saying you're going to improve the agreement, actually it doesn't help a lot. It improves things a little bit out to about 8 months, 8 to 16 months, but after that, there's practically no change. So there's more or less an irreducible error in the model of about plus or minus 2K. And there's not a lot of, there's maybe there's a regional, you could, say that you could define a regional regime because the fluctuations increase to about 4,000 kilometers and then decrease, but okay. But interestingly, if you look at the anomalies, you remove the long-term average and you look at the fluctuations about that. So the models are not converging to the same climate, at least not better than plus or minus 2K. But the anomalies are almost identical in statistical structure in space and in time. So that, in other words, the real world could be a realization of this process if the climate that the model was converging to was different. So if we knew the climate, the long-term average, then the model is actually very good, at least statistically. But anyway, okay. So that's the type of thing. All right. Okay. Right. All right. So okay. So I'll just skip this stuff. There's issues about this. Is just showing the macro weather models converge to macro weather very nicely, for long term. Anyway, okay. So I'll skip right to the end here. Okay. So anyway, this just to. Brief advertisement. This is all contained in this work with Daniel Scherzer that came out a few months ago. All right, so I'll stop there.
I was throwing a remark that people in seasonal forecasting routinely expect that to correct for biases. So they're taking the same message. They think that they have quite a lot of skill, but they need to remove these biases before they calculate the skill. So that seems to fit what you said.
Yeah, no, it does, yes.
And you'd expect a GCM to have such biases because you're doing your best to represent a very complex whole Earth system, and you're never going to bound to be some biases. You just can't expect to get it right. But if you can get reasonably close, then you have the fluctuations would have some skill, and that's what you're saying. So that's quite a nice message, actually.
Mm-hmm. Yeah.
Any other questions? You just first.
Yeah. Okay, it's kind of you found some kind of a time scale separation, like the 10 days weather scale, and then you said it's a micro weather scale between 10 days and 30 years, right?
That's what I'm calling macro weather, yeah.
Macro weather. Okay, I can understand the 10 days is quite clear physically. Berkeley wave cycle is around 2 weeks, but I don't understand about 30 years. What is the meaning of 30 years?
Well, okay. Well, first of all, it seems to be more like 10 years in the industrial period, 10 to 20 years, and more like 50 to 100 in pre-industrial. Okay, so I just showed that briefly, but basically what it is there seem to be slow climate processes which have increasing variability with scale, and then there are high-frequency weather processes that have decreasing variability with scale, and at some point, the weather processes are just weaker than the climate processes. And so when you have anthropogenic forcing, I skipped those slides at the end, but the anthropogenic forcing in the recent period is much stronger than the other, say solar and volcanic forcing. So you could probably forget, the GISS model, for instance, is almost identical whether or not you put in solar and volcanic, as long as you put in the CO2 and the other greenhouse gases, then it actually does a very good job if you do that. But so the point is that it really seems that this transition is a question of low-frequency processes starting to become dominant.
So low frequency means that kind of interaction between ocean and atmosphere. That's what you mean. That's
well, no, but it could be biogeochemical processes even. Because the main candidates, considered the IPCC, for instance, and most of the community, to my knowledge, for variability out to several millennia, the main candidates are solar forcings and volcanic forcings. Okay, I'm forgetting about industrial, greenhouse gases. So, I could show you all kinds of reasons why, at least the reconstructions that they've made so far are unlikely, of solar and volcanic, are unlikely to do the job. And the stuff I just skipped actually shows that when you put these forcings in as best you can, the pre-industrial variability is much too low at the low frequencies. So, we did this with many, many different models for the last millennium, for instance, and the variability is just not strong enough. So it seems that they're going to need new, from the model point of view, they say, fine, we don't have, say, land ice. We know that's a problem, okay. But there are other issues about low frequencies. There are all kinds of processes that are being proposed at very low frequencies, biogeochemical type of stuff, for example. Anyway, so some of these people have proposed and might be important at century and millennial scales. That's what we're talking about. Some of them maybe we haven't discovered yet. But there's also the possibility. This is something Roger Pielke pushes on. But the GCM mindset is that weather is an initial value problem. Climate is a boundary value problem. So you try and model the climate by slowly changing atmospheric composition, slowly changing solar forcing, etc. But actually, you have all these interfaces, and a lot of the time you have interactions across the interface. Of course, obviously the atmosphere-ocean interface is a case in point. So it's not completely clear that this is an adequate treatment of the problem. Well, certainly you could imagine that it might not be so great, whether in practice that's the real issue. I suspect that the real thing is that there are just slow climate processes, and that we just don't have a handle on, because I'm talking about centennial and millennial scale processes.
In your theoretical framework, and cascading, I could understand, of course, the cascading process at quite short time scales. But what is cascading at a much longer time scale?
Well, in fact, with the macro weather regime, you're not getting a cascade in time, but in space. But basically that's a very good question. The way we estimate these statistics with these nice converging lines is we just estimate the fluxes from the fluctuations, and that actually doesn't tell us physically what it is. So in the case in turbulence for the wind field, there's a reasonable theory. When you go to the temperature, it's not so clear. People model the temperature fluctuations using sort of a passive scalar idea, of course in Abukov, but clearly temperature is not a passive scalar. So if you have a passive scalar, then you already have a passive scalar variance flux and an energy flux. So things are already complex, and what you actually have is well, I don't know. We just empirically estimated it, and the statistics are very, very close to within about 0.5% from 5,000 kilometers to smaller scales. This multiplicative structure holds very accurately for all kinds of data and models. Anyway, but that's an unanswered question in general.
Any other questions? Okay, I'll probably suggest informal discussion. Then we've got a lot of things I want to ask. So let's thank Shaun.